6.4 thin lens formula. Okay, previously in the previous topic 6.3 we learned how is it that image is formed by lens, and we learned about two types of lens. We learned about convex lens and concave lens. So we learned that for convex lens, the convex lens can form real image and also virtual image, depend on the distance of the object. Okay, depend on the object distance. And we also learned that for concave lens, don't care where is the object. Okay, no matter where is the what is the object distance, the image will always be virtual. Okay, the image will always be virtual. And we learned that when the object distance change, the image distance will change, and this will also be affected by the focal length of the lens. So here in 6.4 we are going to learn a formula that can relate together focal length, object distance and image distance. Okay, now so look at this experiment 6.3. Okay, so in this experiment, okay, the inference is that image distance is influenced by object distance. Hypothesis: when the object distance increases, the image distance decreases. Okay, we want to study relationship between object distance and image distance for convex lens, and to determine focal length of thin lens using lens formula. Okay, so manipulated variable is the object distance, corresponding is the image distance, constant variable is the focal length. Alright, so we use a convex lens with focal length of 10 cm. Lens holder, 6-volt bulb, wooden block, power supply cardboard with small triangular shape hole, white screen and meter rule. Okay. Set up the apparatus shown in the figure. Okay, switch on the bulb and start the experiment with object distance 15 cm. Okay, and then adjust the position of the screen until a sharp image is formed. Measure the image distance with meter rule and record the reading in a table. Repeat step 2 and 3 with object distance 20 cm, 25 cm, 30 cm, 35 cm. Okay. So before we go into the result, we need to discuss a bit. Why is it that the object distance start from 15 cm? The reason is because the focal length is 10 cm. Okay, the focal length is 10 cm. So if we look at this object distance, 15, 20, 25, 30, 35, basically it's like this. Okay, if this is the lens. And this is the focal point. So this is 2f, double of the focal point. So here to here will be 10 cm. Here to here will be 20 cm. So the first place where the object is placed is here, 15 cm. Okay. And then after that, go to 20, 25, 30, 35. Okay. And then go to 20, go to 25, 30, 35. So what is the first thing is, why is it that we don't put the object at the focal point and also don't have for object distance of less than the focal length? The reason is because if you put object here, okay, image will be virtual. Okay, if you put the object anywhere here from the focal point until the lens, anywhere between the focal point and the lens, okay, image will become virtual. So if the image is virtual, that means the image cannot form on a screen. Okay, you will not be able to see image on screen. So if you cannot see image on screen, that means you cannot record the image distance. So that is why in this experiment, the object distance is after the focal point. Okay, the object distance is longer than the focal length. This is so that we can get real image. Okay, get the idea. Okay, anywhere lah. Okay, start from here and beyond, we will be able to get real image. Okay, so this is the main reason lah why like that. Okay, Okay, so the result here. So what we are going to be able to see is that as the what we are going to see is that at first the image is going to be large. Okay, the image is going to be big. Okay, image is going to be big. That means this one will be big. And then at 2f here, that means as the object moves further away, at 2f, the image will be same size as the object. And then after 2f, the image will be smaller. Okay, image will be smaller than object. Further and further away, image will get smaller and smaller and smaller. Okay, so this is what we are going to see lah. So when the image is smaller and smaller and smaller, the image distance, what will happen to the image distance is that the image distance will also get nearer and nearer. Okay, the image distance will become nearer and nearer to the lens. That means become smaller and smaller lah. Okay, become smaller and smaller. So that means this one, when it is near, this one will be long. Okay, the image distance will be long, and when the object distance is getting bigger and bigger, the image distance will become smaller. Okay, smaller and smaller. Okay, so analysis of data, plot a graph of 1 over v against 1 over u. Okay, so the graph that we are going to get will look like this. Okay, 1 over v, 1 over u. Okay, the unit is in this case, because it is in centimeter, so this will be per centimeter. This one also per centimeter. Alright. So the graph will look like this. Okay, this is what the graph is going to look like. Alright, and when you get the gradient, okay, when you get the gradient of the wait a minute. And what is it that we will find is that from the straight line equation, y equals to mx plus c. So y is 1 over v. Okay, x is 1 over u. Okay, this one, the gradient, what the gradient is going to be, it is going to be negative 1. Okay, it will become negative 1. That is the gradient for this graph. Okay, going to be negative 1. And then this y-intercept, we will find that the value is the same as 1 over the focal length. Okay, 1 over the focal length. So if we rearrange this equation, then we will get 1 over f equals to 1 over u plus 1 over v. Okay, we will be able to get this equation. Okay, so from this equation relate together the focal length, object distance, and image distance. So that means that if we just use this formula, then we can calculate the object distance, and if we know the focal length of the lens and we know the object distance, we can know the image distance. We can know where the image is going to appear. And one thing that is very good about this formula, this is the thin lens formula. When we talk about thin lens formula, this is the thin lens formula. So another good thing about this thin lens formula is that not only we can find the image distance, but we can also determine the characteristic of the image from the information in this thin lens formula. Okay, we can also find out the characteristic of the image. Okay, so later we will see how we do that. Okay, so thin lens formula can be used to solve problems regarding lenses. Okay, so for example here it says that position of camera lens close to object produce a larger image. So if we want to produce a larger image, then we can move the lens closer to the object. That means we make the object distance smaller, then we can make the object look bigger. But how is it that we know that it can make the object look bigger? Okay, this is through calculation of the image distance. Okay, just by calculating the image distance, we can find out whether the object is going to become bigger or smaller. Okay, so this one, position of camera lens far from object produce a small image. Okay, small image. Far from object produce small image. Okay, so how do we use this thin lens formula? Okay, so this is very important. This table is very important. Okay, when we are using convex lens, the focal length of the convex lens, we must put a positive value. Okay, if it is concave lens, the focal length we need to put negative value. So that means Okay, that means if we have a convex lens, okay, if this is 10 centimeter, so when we want to put inside the formula 1 over f equals 1 over u plus 1 over v, we must put in negative 10 inside here. Okay, we must put in negative 10. This is convex, so we put positive 10. But if it is concave lens, okay, if it is 10 centimeter concave lens, so that means we need to put in negative 10. Okay, like that lah. Okay, now for the image distance, okay, for image distance, if the image is real image, then the image distance we put positive number. Okay, positive. Okay, and or okay, if the image is on the opposite side of the object, okay, on the opposite side of the object, then it is positive. Okay, or we say lah, okay, on the opposite side of the object, then we put positive. That means, for example, if we have okay object here, okay, for example like this. For example like this, okay, the image is here, for example. Okay, this one is image. So let's say that this image distance is 30 centimeter. So we put inside here positive 30. Okay, but for this one, okay, for this one, okay, let's say the image is the object is here. Okay, so the image is here. Okay, image is here. This is the object. Okay, image is here. So let's say that the image distance is let's say 7 centimeter. So this 7 centimeter, when we want to put inside here, we put as negative 7. Okay, we put as negative 7. Okay, negative 7 inside here. So this is for virtual image. Okay, virtual image we put negative. Okay, virtual image negative. Or if the image is on the same side as the object, then we put as negative lah. Okay, because if on the same side, then it's definitely virtual. Okay, this is also something that we learned in a previous topic. In the previous topic, we learned that all of the real image, okay, all real image, okay, is inverted, and all real image is also at opposite side. Okay, that means opposite here lah. Okay, all real image is definitely inverted and opposite side. All virtual image is upright and also same side as object lah. Okay, so this is a very important characteristic for lens. Okay, the lens, all real image inverted at opposite side, all virtual image upright same side. Okay, this apply for both lens. Don't care whether it is a convex lens or it is concave lens. Okay, it's the same. Okay, let's look at example. A thin convex lens has a focal length of 12 cm. Determine the characteristic and position of the lens of the image form and linear magnification when the object distance is 18 cm and 4 cm. Okay, so it says that the convex lens is a convex lens, focal length 12 cm. So because it's convex lens, so the focal length we will put positive. Okay, and then it says that the object distance is 18 cm. So from 1 over f equals to 1 over u plus 1 over v. So this one, the focal we put 12. Object distance is 18. So we want to calculate the virtual image. Calculate the image distance. Okay, we will find that the image distance is 36 cm. Okay, one thing that is very important is after you take this and minus this, remember to take 1 and divide with the answer. Okay, a lot of students they make the mistake of forgot to divide. Okay, this one 1 over v, this one at the top, they forgot to take 1 and divide with the answer. Okay, so here we see that it is positive 36 cm. So what is the image characteristic if it is positive 36 cm? Okay, so what we know is that so usually first we want to, when we talk about image characteristic, we will want to know the first characteristic is whether the image is bigger, whether got magnification or not. Okay, is it bigger than the object, same size as the object, or smaller than the object? Okay, so how do we know whether it is bigger, smaller, or same size? Okay, we look at linear magnification. Okay, linear magnification. So how do we calculate magnification of image? Okay, how do we calculate the magnification? Okay, the formula to calculate the magnification is image distance over object distance. Okay, image distance over object distance. So image distance is 36 cm over the object is 18. So that means 2 lah. Okay, so if it is 2, it means that the image is larger than the object. Okay, the image is larger than the object. So the first characteristic is that it is magnified. Okay, image is magnified. Second, if this one you see the image distance is positive. If positive, okay, you see real image, then is positive. So that means the if the image distance is positive, so this means that the image is real image lah. Okay, that means the image is real image. And if it is real image, it means that it must be inverted. Okay, the image must be inverted. Okay, because all real image is inverted. Okay, all real image is inverted. Alright. So the last one is the position. We want to know the position of the object. Okay, so the position, where is it? You see, this is the focal. When we talk about position, of course, the first thing is we give the image distance lah. Okay, so image distance is 36 centimeter, and then the position is beyond 2f. Okay, beyond 2f. That means more than double the focal length. Okay, and is the image on the same side as the object or on the opposite side? How do we know? You see that this is real. So if it's real, that means it's on the opposite side of the object. On opposite side of object. Okay, and then after that, okay, we do the B. Okay, when it's 4 centimeter, same thing, 1 over f equals to 1 over u plus 1 over v. So the focal is 12 centimeter. Positive 12 because it is a convex lens. Okay, object is at 4 centimeter. So what will be the image distance? Okay, we get that it is negative 6 centimeter. Okay, so the magnification v over u. So v is 6, and object distance is 4. Okay, so that means we have 1.5. Okay, magnification is 1.5. So if the magnification 1.5, so the characteristic of image is magnified lah. That means larger than the object, and we see that the image distance is negative, so this means that the image is virtual. Okay, and if it's virtual, that means it must be upright lah. Okay, because all virtual images are upright. Okay, now for the position, image distance is negative 6 centimeter between not between, sorry. Correct. Yeah, between F and optical center on the same side. Okay, same side as object. Okay, we can get a lot of information from a thin lens formula just by knowing the type of the lens, and we know the image distance. We can know the characteristic of the image. We know where is the image going to appear. We know whether it is a virtual image or real image. We know whether it will be bigger, same size, or smaller. We know upright or inverted. Okay, so there are a lot of information that we can get. So that means if we know this thin lens formula, then we can get the characteristic of the image very quickly lah. Okay, we don't need to draw the ray diagram. Okay, the ray diagram takes more time. Okay, a bit of information for linear magnification. Okay, for linear magnification. Okay, linear magnification is where we want to see, we want to represent by using a number what is the size of the image compared with the object. So the original at first is we use the height of the image divided by the height of the object. Okay, we use the height of the image divided by the height of the object. Oh, sorry, I think I used the wrong symbol. Okay, I think I better write the word lah. Okay, image size or the height over the object size or the height. Okay, and then we found that the ratio, okay, between the image distance also the same as the object distance. Okay, the image distance over object distance also can get the same number, okay, the same magnification. So that's why we can calculate the linear magnification by using image distance over object distance. Okay, okay, so another thing that we need to learn in regarding formula that have something to do with lens is the power of lens. Okay, so how do we calculate the power of lens? Okay, if the lens can bend the light more, then that means it is more powerful lah. So for example, okay, we have this lens and this lens. Okay, so this lens, the light go in here, and the light refract like this. Okay, compared to this one, okay, light go in, and the light converge, bend and become like this. So which one is more powerful? Lens A more powerful or lens B more powerful? So the answer is lens B is more powerful. Why B is more powerful? Because it can bend the light more. A only bend a little bit. B can bend the light more than A. So B is more powerful lah. So how do we know whether a lens is more powerful or less powerful? We can just know by looking at the focal length. So as you can see, if it is less powerful or if you bend the light a little bit only, then okay, the focal length will be longer. Okay, the focal length will be longer. So this is the focal point, right? Okay, light come in parallel, pass through, and then it will converge to one point. So that point is the focal point. So the distance between the focal point to the optical center of the lens is what we call the focal length. Okay, so if the lens is less powerful, then the focal length will be longer. If it is more powerful, then the focal length will be shorter. Okay, so this is the same thing for concave lens also. Okay, this is the same thing for concave lens. So if the light go in like this, okay, let's say this one, okay, only bend a little bit. So this is the focal point. Okay, the light diverges like this. So this is the focal point. So compare with this. Okay, light parallel come in. Okay, so it looks like the focal point is here. Okay, the focal point is here because it looks like the light come from this point. So again, as we can see, this one here to here, this is the focal length. This one here to here, this is the focal length. So we can see that okay, let's say this is lens C, this is lens D lah. So we can see that lens C is less powerful than lens D because lens D can bend the light more. Okay, it can bend the light more. So D is more powerful than C. So same thing also, we see that the focal length of less powerful is longer than more powerful lens. If the lens is powerful, then the focal length will be short. Okay, focal length will be short if the lens is more powerful. All right. Okay, so how do we calculate the power of lens? Okay, the way we calculate power of lens is we use the equation 1 over the focal length, and the focal length must be in the unit of meter. Okay, the focal length must be in unit of meter. So let's say that this focal length is 20 centimeter. This is 10 centimeter lah, for example. Okay, And then what is it that we can get is 1 over, if 20, for example, this is the power for lens A. So 20 centimeter, change to meter, so this is 0.2. Okay, so we get 5. Okay, the unit for the power of lens is diopter. Okay, diopter. This is the power of lens. Okay, for lens B, 10 centimeter, so 0.1 meter. Okay, so it's 10 diopter. Alright. Okay, so for concave lens, okay, let's say this is same also. Let's say this is 20 centimeter. This is 10 centimeter. So for concave lens, the focal length must be negative. Okay, same like in the lens formula. Okay, so that means this is negative 20. Okay. Okay, so this is negative 5 diopter. Okay, 1 over negative 10. Because this is concave lens, we put negative. So it is negative 10 diopter. Sorry, 10 centimeter. Sorry, this one should be 0, must change to meter, sorry, 0.2 meter. This one is 0.1 meter. Okay. Okay, example 2. An object with a height of 9 centimeter is placed 60 centimeter from a concave lens with focal length of 30 centimeter. Determine the position, size of the image form. State the characteristic of the image form. Okay, so 1 over f equals 1 over u plus 1 over v. Okay, so this is a concave lens. Focal length is 30 centimeter. So we put negative 30. Okay, so the object distance, it says that place 60 centimeter from a concave lens. Okay, place 60 centimeter from a concave lens. So that means the object distance is 60 centimeter lah. So 60 plus, okay, the what is the image distance? Okay, we get negative 20 centimeter. Alright, so characteristic of image. Okay, wait, we calculate the magnification first. Okay, so the okay, so here it doesn't ask for the linear magnification. Okay, but we can calculate, but we need to calculate the size of the image. So we use image size. Image size over object size. equal to the because this we can get the linear magnification with this, and the image distance over object distance also can get the linear magnification, so we can put this as equal lah. So the image size over object size says that the height is 9 centimeter. Okay, now the image distance is 20 centimeter, and then the object distance is 60 centimeter. So the image size, it is 3 centimeter. The image size is 3 centimeter. So the image characteristic, image is whether it is bigger or smaller or same size. Height is the object size is 9 centimeter, image size is 3 centimeter. So that means image is diminished in size. Diminished in size, and then this is negative. The image distance is negative, so we know that this is virtual image. Image is virtual. So whether it is upright or inverted, we know that it is upright. How we know that it's upright? Because all virtual images are upright. All virtual images are upright. And then the position, negative 20 centimeter. Negative 20 centimeter. At between focal, just F lah. Between F and optical center. Between F and optical center, because the focal length is 30 centimeter, the image distance is only 20 centimeter, so it's less than the focal length. Between F and optical center, same side as object. How we know that it's same side? Because all virtual image are same side with the object. All virtual image same side as object. So here we have all the answer that the question want. It says determine position, so this is the position. They want us to determine position, the size of the image, and characteristic. So where is position? This one. This part is where we talk about the position. The answer for position. Answer for size, this one. Size of image. And then the characteristic. This one, all of this is the characteristic. Characteristic of the image. Okay, so we fulfill everything that the question wants. Okay, next, figure 6.37 show a straight wire placed along the principal axis of a thin convex lens with a focal length of 12 centimeter. X and Y are 24 centimeter and 18 centimeter apart. Okay, 24 centimeter and 18 centimeter respectively from the lens. So this one X is 24 centimeter. Okay, here to here is 18 centimeter. Okay, so it says cricket take 6 seconds move from X to Y. What is the speed of the cricket's image? Okay, if we want to know the speed of the cricket's image, then we need to know the changes in the position of the image. Okay, so that means we need to calculate the image distance when the cricket at X and image distance when the cricket is at Y. Okay, so 1 over F equals 1 over U plus 1 over V. Okay, focal length is 12 centimeter, so positive 12 because this is convex lens. Image distance 24 centimeter. Okay, we want to find the image distance is how much? Okay, it is 24 centimeter. Okay, 24 centimeter. Okay, so next we calculate if at Y, what is the image distance? Okay, 12 centimeter. This is 18 centimeter. Okay, we get 36 centimeter. Okay, so that means the image of cricket go from 24 centimeter to 36 centimeter. So distance traveled by image is okay, this is 12 centimeter and the time it takes is 6 seconds. So okay, distance over time, so the distance is 12 centimeter. The time is 6 seconds. Okay, so 2 meter per second. Oh wait, got problem. Okay, this one is 12 centimeter. So this should be 2 centimeter per second. Per second, not per second, per second. Okay, got mistake here. Okay, next exercise number 1. Okay, a concave lens with focal length of 25 cm form a virtual image of an M at a distance of 20 cm from the optical center of the lens. What is the original position? So what is it that it wants here is the object distance. Okay, they want the object distance. So 1 over F equals to 1 over U plus 1 over V. Okay, so because this is concave lens, focal length 25 cm, so negative 25. Okay, the object distance, okay, is the one that we are looking. This one is the, okay, this is of 20 cm. Okay, and this is virtual image, right or not? Okay, it says that it's a virtual image, so that means the image distance must be negative 20 lah. Okay, if it's virtual image, then the image distance we put negative. So we get, okay, so object distance is 100 centimeter. Okay, 100 centimeter. Okay, D. Draw a ray diagram to show the formation of a virtual image of the end. Okay, so in SPM, if ask you to draw ray diagram, so all you need is just use your ruler, pencil, and draw. Okay, if come out in question, they are not going to provide you with the graph paper. Okay, so you just draw on white, okay, on the white piece of paper. Okay, so first thing that we do is we draw the principal axis. Okay, we need to draw the principal axis. After principal axis, we draw the lens. Okay, the lens. Okay, so the position of the focal point, you don't have to measure exactly. Okay, don't have to measure. Okay, it says that the focal length is 25 centimeter and the image distance is 20 centimeter. Okay, and we know that the object distance is 100 centimeter. So what is it that we need to do is we just roughly ratio lah. Okay, ratio roughly. Okay, roughly where is the object and image. So okay, if this is 25 centimeter in focal point here, that means this is 25. So that means here is 50 centimeter. So that means here is 150. Sorry, that means this is 75, and then this one will be 100 lah. Okay. So that means this object is over here. Okay, object is here. Although you don't have to measure exactly, but the ratio, it must look like more or less the same. Okay, it must look more or less the same. Okay, so let's draw the ray diagram. Okay, here is the F. Okay, this will be 2F. Okay, so let's draw the ray diagram. So the first line, parallel in. Okay, and then the second one. Hey, wait a minute. Oh, lama. Wrong. This is concave lens. Oh my god. Sorry. concave. Okay, concave lens. Okay, so like first one that come in parallel. Okay, the light will come from the diverge from the focal. Okay, so the line number 2 pass through the center. Draw arrow before and after. Okay, so where will be the image? Okay, the image should be here. Okay, so this image, this is object. Okay, I think that's all. Okay, everything is there. Okay, everything is there. Okay, so this is the ray diagram to a ray diagram for the formation of virtual image of the end. Okay. Okay, next, a small bulb is at a distance of 1.6 meter. Okay, 1.6 meter from the screen, and a thin convex lens with a focal length of 30 centimeter is placed between bulb and the screen. Okay, so what information that we have? If we want to, we can organize for this kind of question. Actually, for the previous question also, okay, we can organize the information that we have just by write out the information that we have. Okay, it says small bulb at a distance of 1.6 meter from the screen. Okay, that means is like this. Okay, that means we can draw also to help us. Okay, this is the screen. This is the bulb. Okay, so here to here is 1.6 meter. Okay, thin convex lens with focal length 30 cm placed between the bulb and the screen. Okay, convex lens. Okay, the focal length is 30 cm. Okay, determine two positions of the convex lens that can produce a sharp image on the screen. Okay, so if we want to produce sharp image on the screen, that means the total, that means the object distance plus image distance must equal to 1.6 meter. Okay, that means this is what we want. That means the object distance plus image distance equals to 1.6 meter. Okay, and within this 1.6 meter we need to determine two positions Okay, where is it that we can put the convex lens in order to produce sharp image on the screen? Okay? Okay, so from 1 over f equals to 1 over u plus 1 over v. Okay, so this is okay. We modify a bit. So this is v. Okay, v plus u. Okay, over uv. Why like that? Because this one u multiplied by v, so this one 1 multiplied by v lah. So this one v multiplied by u, this one 1 multiplied by u, so v plus u. Okay, over uv. Okay. Alright, so here that means this one is 1.6 meter. Okay. F, the focal length is 30 centimeter. Okay, 30 centimeter. So we change to meter, so that is same as 1.6 meter. So it's 0.3 positive because it's convex lens. So this v plus u is the same as u plus v, so equals 1.6 meter. So uv equal to, okay, this is equal to 0.48. Okay, 0.48. All right. Okay, so this is okay. This is equation 1. This is equation 2 lah. Okay, so okay, from equation 1. Okay, u plus v equals 1.6, so v equals to 1.6 minus u. Okay, so substitute v into 2. Okay, so we get u 1.6 minus u equals 0.48. So we get 1.6 u minus u squared equals to 0.48. Okay, so we can get the equation. Okay, u squared minus 1.6 u plus 0.48 equals 0. Okay, so we need to factorize this one lah. Okay. Okay, so we can use the formula for factorization. So this one u, so u equals to okay, minus d negative d plus minus b square minus 4ac square root over 2a. Okay, yeah, I think this is it. Okay. Okay. Yeah, okay. So negative. So negative 1.6 plus minus, okay, this one is 1.6. Okay, negative 1.6 square minus 4, 1, this is 0.48. Okay, over 2, okay, 2a. Okay, let me check, make sure everything is correct. Okay, I think correct. Okay, so we should get, okay, so we have 1.12 meter for 1.2, okay, 1.2 meter, okay, 1.2 meter. Okay, another one is 0.4 meter. Okay. Okay, sorry it takes such a long time. I key in the calculator wrongly and got problem, so take a very long time. Okay, the two object distance are at 1.2 meter and 0.4 meter. Okay, like that.